We need to talk about stress concentration and how cracks propagate. I don't know if you've seen this picture of it. This was a tanker in World War II which split in half before it ever set sail, and it was due to stress concentration. Now, you can make a sort of a map of stress in a piece of material, like you make equal spaced lines, kind of like a contour map. So let's say each one of those lines is 1 psi, just for example. So 1 psi running through the thing. When you get to a notch or some discontinuity in shape, all those stress lines still run through the material, but they get squeezed together closer where that notch is. They get squeezed close together around holes, so you get stress concentrated around holes and against sharp corners. These are pictures of stress lines. It turns out that stress especially concentrates at sharp corners. So an inside corner or a notch, stress concentrates there, and we call that stress concentration. We also call it a stress riser, because the stress rises. So people will talk about stress risers in the corner. And around a crack, stress especially rises. Here are some pictures of stress trajectories around a crack and an illustration of what's happening at the molecular level. There's a formula you can use to figure out how much the stress concentrates at a sharp corner. So here's the general formula. You don't need to memorize this. It's just kind of interesting to see. So here's the general formula: 1 + 2 radical half of the length divided by the radius at the tip of the crack. Okay, fine. So if you have a 4-inch hole, you plug numbers into that equation, and you find out that the stress around the hole is 3 times higher than it is in the rest of the plate. If you have a 4-inch long crack with let's say a radius of 1/1000th of an inch, and you plug those numbers in, you find out that the stress around the tip of the crack is 90 times greater than it is in the rest of the plate. Our problem is that all material contains cracks. A lot of the cracks are microscopic in size, but they're there because no material is perfect. And if the crack gets bigger than a certain critical size, that crack starts to spread. We say it propagates, which is another way of saying it spreads. And that especially happens at sharp corners. At the end of a crack, and a crack corner just makes that worse, at the end of a crack, the radius can be tiny, tiny, and you might wind up with a stress concentration at the tip of the crack 1,000 times higher than the stress in the rest of the material. So it's a big deal. You might have illustrated this if you've ever used a glass cutter. A glass cutter looks like this. They're real cheap, I mean inexpensive, got a little wheel on them, and you just run the wheel in a line along the surface of the glass. You don't have to press hard. You just press enough to make a scratch, that's all. And then you put the piece of glass over the edge of a table and push down, and it cracks right along that straight line with the scratch you just made. Why does that work? Because you have created a crack where there's a stress concentration at the tip of the crack. It's a very small radius there, and it doesn't take much force out here at the end to cause that crack to propagate. This is a perfect example of how that works. I took this photo I was at a conference, and this was a motel. They had a coffee maker with a glass carafe in it and a warning that said, "Do not use if the carafe is chipped or cracked." Why? Because cracks will propagate and the thing will break. You'll notice if you've been in a hotel lately, they now use metal coffee makers for that reason. So anyway, what you need to think about as a designer is that sharp corners create stress risers. They create stress concentrations. And so if you are having to cut a hole in something, you want to reduce the amount of stress concentration. You want, if you make a hole, you want the corners to be round, just as round as possible, not sharp. Sharp corners create stress risers and cause cracks to propagate, so never do that. Here's a sink installer. She cuts rounded corners in the opening in the countertop. If she were to cut a sharp corner, well, that is a recipe for a stress concentration, especially if somebody does something like use the counter as a stepladder and stand on it, the thing will just crack. Crack propagation causes avalanches to break off. It causes cracks in the polar ice up at the North Pole. It causes glaciers to calve off in Antarctica. Crack propagation is an issue in concrete, and what we're worried about is if we don't get the water mix right and we get little holes in the concrete mix, they can be sharp cornered little things and cause stress risers, and then you have weak concrete. You may have seen people doing crack repair in metal parts. So here is a welder who is filling a crack in some kind of round tube thing. What they do is they drill a round hole at each end of the crack first. And you can probably easily imagine, oh, that greatly increases the size of the radius. So before we had a crack with a microscopic radius size, now we have a crack with a radius that we can measure in fractions of an inch, much lower stress concentration. Now we come in and do some welding. I don't know if you've ever seen an impact tester machine. We use them for various kinds of materials, including plastic and steel. Here's an impact tester for plastic, and what they do is they take a sample piece. ASTM has standards for how big the sample has to be and how you cut the notch. And you can cut a notch and stick the thing straight up and down here. Then you pull this hammer up in the air and let go of it, and it swings down and breaks the thing due to crack propagation. Charpy is similar, but it's got a different orientation. So plastic materials charts list the notch sensitivity of a particular kind of plastic. How vulnerable is it to crack propagation? Well, we think about that with steel too. And here is an impact tester that is out in the metallurgy lab at LCC, out in the fabrication and welding program. So this arm has a very heavy weight on the end. Here it is pulled up. Here in the next picture, here it is, it's been released. And so what they do is they put, in this case, it's a metal sample down here, and they calibrate, okay, how much force are they going to let this release with, and see how much force it takes for this sample to crack. Last thing I want to mention is about a thing called FEA, or finite element analysis. First of all, before going there, we can view stress concentrations in a piece of material using a polarized filter. They're not cheap, but we can look at them in a lab and actually see these lines of stress concentration. Here's a plastic protractor like you'd use in school, and you can see the lines of stress accumulating around the sharp corner. Well, we can use software to quantify that. And CAD is great, it can draw shapes for us, but we need another kind of software if we're going to predict how great is the stress at a particular point in our thing that we drew. And so we'll use a simulation software known as FEA, which stands for Finite Element Analysis. The reason it has that name is that the software, and SolidWorks has a software like this, Inventor has a software like this. The software looks at the geometry that you drew, the solid model, and it breaks the solid model into small triangular elements. And it's called finite because they're finite in size. It's not just a continuous analog, a continuously changing thing. These are little triangular sections, and the software could go in and calculate the stress in just that finite section. Then it moves to the next section and it calculates the stress in that section, and so on and so forth. And then it puts them all together and gives you a readout. It gives you a report with a bunch of numbers, but it also gives you a picture where it displays the stress with color coding. Here's simulation add-on package out of SolidWorks, and if you have color blindness, this may or may not be easy to see, but there's red at the top for the highest stress, blue at the bottom for the lowest stress, and here is SolidWorks mapping the stress concentration in the bottom of a threaded bolt. Here's a stress concentration in a vice grip, and then here are some bolted connections in some kind of generator or coupling or something. I think SolidWorks has includes FEA with its general SolidWorks package, and it'll do some calculation. To do the fancy stuff, you need to pay a little bit more. So that's FEA, Finite Element Analysis.